Hello, everyone. You're watching the Summit of Things, and this session is AIoT needs both learning and reasoning. And I'm your host, Tiffany Nielsen, and today we're diving into a rich topic at the intersection of artificial intelligence and the Internet of Things, or IoT. And with me is Dr. Scott Gerard, an expert who has been exploring AI in its many forms for decades. Scott, thanks so much for joining us once again. How are you today?
I'm great, Tiffany, and I'm really excited to be here talking about how AI is evolving, especially in the context of IoT.
And where are you joining us from, Scott?
I'm from Raleigh, North Carolina.
And is there anything else that you wanted to share about your background or an expertise or knowledge reactor?
Just that we do a lot of work for artificial intelligence and machine learning for all kinds of different people, different clients, and I think it's the future, and we're going to cover that in some of this session.
Perfect. Thank you, Scott. And let's start with some history. When people think of AI today, they often imagine neural networks and deep learning. But you point out that the first few decades of AI was focused on something else, reasoning. What do you mean by that?
Well, AI didn't start with big neural networks and massive data sets. In the 50s and in the 80s, the field was really dominated by what we call symbolic AI, or the term GoFi, which stands for good old-fashioned AI. That's the kind of AI people were doing. And researchers built these systems that use logical rules to represent knowledge and perform inference. Think about expert systems, their improvers, planning algorithms, that kind of thing. The idea was to encode human knowledge in this formal logical language and then have the system reason logically about that. And there were some impressive successes, but there were also some notable limitations.
And what were those limitations, Dr. Scott?
Well, symbolic reasoning systems can be brittle, and they require you to know all the rules ahead of time, all the logical rules, which is tough because the real world is noisy and it's messy. Reasoning can handle crisp logic, but it struggles with the uncertainty and nuance in the real world. And they don't really scale well when you have to cover thousands of different potential scenarios.
Well, that's where learning comes in, right? And how did AI shift towards learning in recent decades?
Well, starting in the late 80s, but really taken off in the 2000s, machine learning became the dominant approach. So instead of hand coding all these rules, we feed algorithms lots of data and then let them discover the patterns. And that's why the term big data only became popular in the last 20 to 25 years. Learning algorithms, and especially neural networks, need data to learn their parameters. And the more data you have, the better these models perform. In contrast, reasoning algorithms really don't need any data. They all they need is domain knowledge and the rules to work with.
Thanks, Dr. Scott. So we have two extremes: AI doing reasoning without much data, and modern AI doing lots of learning with tons of data. And so, what are the strengths and weaknesses of each?
Well, reasoning is really cool and it excels at structure and consistency and interpretability. So if you know the rules of a domain, a symbolic system can really ensure that those rules are never violated. And it's great for safety critical applications. But it is limited by what you can explicitly encode. Learning, on the other hand, is very flexible. It can find patterns you didn't even know existed and handle, really high dimensional sensory data like images and sensor streams. But it's often kind of a black box and can't make mistakes, and it can make mistakes if the data distribution changes. And it also needs lots of data, like you mentioned, and it can be computationally very expensive in certain cases.
Thank you, Dr. Scott. And which approach do you suggest for IoT developers and project managers to choose for their next project, learning or reasoning?
That is a great question, but my answer is you need both. For many real world problems, both are necessary. Neither alone is sufficient. especially in IoT, where the devices are interacting with the physical world. You need reasoning to enforce the constraints and domain knowledge that you know you have to maintain, but you also need the learning to process the noisy sensor data and adapt to all the changing conditions.
Well, that makes sense. IoT devices often make decisions in the wild, sometimes with limited data and other times with complex rules. So, can you share some examples of how to combine learning and reasoning?
Absolutely. And that's kind of the key element here. The whole field emerging around this, some people call it neurosymbolic computing. And there are researchers trying to figure out how to integrate these neural networks and logic in really tight and principled ways. The idea is to get the best of both, right? You want the pattern matching power of neural networks, and you want the structure and interpretability of symbolic reasoning. But to be honest, the neurosymbolic stuff is still a little immature, and I don't think it's really ready quite for prime time yet. However, I do think the name symbolic reasoning is good. It's still a little bit too limiting. There are some very effective learning algorithms that are not based on neural networks at all. XGBoost is a common winner in some of these Kaggle competitions. It's a learning algorithm, but it has nothing to do with neural networks. And when it comes to reasoning, there are a lot of reasoning algorithms that aren't symbolic. Scientists have been reasoning with equations for centuries, but equations really aren't symbolic in the same sense that the neurosymbolic guys use them. So, what I've done, hold your horses, I've invented this term Lerno-Resonic AI. So it's Lerno-Reasonic, Lerno-Resonic reasoning. And the idea is that I want to include not just neural networks and symbolic reasoning, but I want to include some of these other approaches that are really valuable today. Now, I'm sure that our audience is rolling their eyes at this point, and they should be. I just find the term Lerno-Resonic to be very pretentious, and I'm sorry about that, but it's the only term that I could come up with that really tried to capture all of these ideas that I wanted to include. The one thing I will say about it is if you imagine that each of these algorithms that I mentioned is an arrow to solve some kind of an algorithmic problem, then I assert that my lerno-resonic quiver of arrows is bigger than just a neurosymbolic quiver of arrows. Uh, Maybe a little pretentious there too, but that's what I'm trying to do.
So, Dr. Scott, you mentioned that some of this may not be ready for prime time just yet. So, what is possible today?
There's a number of different patterns that I kind of see that I think will work pretty well. I've implemented some of them. The patterns basically try to orchestrate these different elements together, and many of them are pretty simple, and they're certainly less tightly integrated than some of the research grade neurosymbolic approaches. One that I think is particularly interesting, particularly for AIoT applications, is just a simple pipeline. The first stage is you feed the messy, noisy real world data into it, like images or natural language text. Those are learning algorithms, and they extract the symbols of interest that they find in that input. So now we've converted this learning algorithm has converted me to symbols and equations. Then you use some kind of a rule-based reasoning component to enrich those symbols with some additional symbols. So if you know that A always implies B and you find an A, well, then you can necessarily add B to your list. Some of these rule-based systems can help you in that sense. We're not trying to do everything with the rule-based systems, but they can help out. And then the third step is, well, let's do a tabular learning algorithm to look for patterns in that enriched symbol set. So now we've got learning and reasoning and learning all going together to do some interesting things. And I'm building that kind of a system right now with one of my projects. Another promising area is something called physics informed neural networks. They're called PINs, PINN. So let's imagine you're trying to model some fluid flow through an IoT connected pipeline. Well, the Navier-Stokes equation describes fluid dynamics very well, but the Navier-Stokes equations are notoriously hard to solve numerically. So what you do with pins is you train a neural network on the sparse data that you get from the sensors of the system that you have, and that may be things like pressure and flow rates. And then you add a term to the neural network loss function that penalizes the network when it violates the underlying physics equation. The result is a model that not only fits the data, but it also respects the physics. It blends the reasoning, the equation, with the learning, the neural network, in a way that's practical today. People are actually using these pins today.
Thanks, Dr. Scott. And are there other approaches? I know you've mentioned vibe coding in the past.
Yes, I think vibe coding is a very interesting way to approach some of these things. For those who don't know, it's getting very popular these days. And this is where a developer uses an LLM and he prompts it with what he's trying to do. And he gets the LLM, which is a learning component, to design some other system components. And that the output of the LLM is then either rules or code or something like that. But that is a reasoning component. So a learning component is building a reasoning component. There could be bugs in it, but it's a good start. This is also a Lerno-Resonic approach. I'm combining learning and reasoning together into one thing. Once you have the reasoning components implemented in your code, you can test them in a simulation system of your system. Then at runtime, you would use reinforcement learning algorithms. They will learn how to control the system through a series of rewards and constraints. So that's another kind of interesting way to do it that is based on this whole new idea of vibe coding with LLMs.
Thanks, Dr. Scott. It's fascinating and confusing at the same time. So let's make sure I'm following along correctly. So the LLM is helping you explore ideas, but you're validating and refining them with rule-based reasoning in the simulation.
Exactly. The vibe coding is using the LLMs, a learning component, to generate some reasoning components. And those are rule based systems or code based systems. Once we have the reasoning components, then we make a simulation and it we validate that the system is actually doing what it's supposed to do without violating physics and without violating logic.
Thank you, Dr. Scott. And so let's bring it back to IoT. Why are these hybrid approaches particularly relevant for IoT developers and project managers?
Anybody who's paying attention knows that these LLMs in particular hallucinate, and sometimes they just go completely off the rails, even though they're very confident about their statements that are totally wrong. So, learning systems aren't perfect, none of them are, and they do make mistakes. Now, a text mistake on your desktop is one thing, but mistakes in the physical world can be both expensive and dangerous. So I've kind of got some things that I like to encourage developers to consider. And the first is um, simulate your IoT systems before you physically deploy them. And the goal is to gain confidence that the system you're building will perform as you expect once you do actually physically deploy it. I also encourage people to implement guardrails, and the guardrail should be implemented in reasoning components. And those reasoning components should wrap around the outside of and be external to the learning components. So when the learning components do crazy things, the reasoning component can say, nope, I'm not going to accept that. So the reasoning guardrails could be containing actions to be within certain predefined acceptable ranges or various other things like that. And now we can't enforce all possible constraints with reasoning guardrails. If we could, we would just build the whole thing with reasoning engines, but we can't because that it's too complicated and too messy. But we can certainly eliminate a large number of problems And if the system does go off the rails, you could go back to the reasoning components and say, this is where I need to change it because it's making a mistake. And then the third thing that I would recommend is I definitely encourage people, developers, supporting to support human in the loop interfaces. Humans are your last line of defense if the AIoT system ever starts acting weirdly. Without human in the loop designs, the humans, your buyers, won't have the confidence to even try your systems. So it's good to give them a way to see what's going on and to control it if it needs to. And plus, the humans are a great source of valuable feedback.
Dr. Scott, you refer to humans as if you're not one. Are you really a robot?
I refuse to answer that question.
If you have questions just like mine, feel free to drop them in the chat. Dr. Scott will be available after this to answer your questions. But let's look ahead. What do you see as the future of AI and IoT? And do you think that we'll see more more acceptance of these hybrid systems?
Absolutely, I do. I really do think it's the future of AI. As AIoT deployments become more complex, and I'm thinking of precision agriculture, smart cities, autonomous vehicles, that kind of thing, we need AI systems that can adapt quickly, but we also need them to respect various constraints. So pure learning isn't enough, and pure reasoning isn't enough. I think the future must combine both of these. And I expect we'll see more research turning to use these Lerno-Resonic ideas into practical tools. More frameworks like pins and various kind of hybrid reinforcement learning. We'll also see a lot more emphasis, I think, on human in the loop AI and where IoT devices ask uh, if an IoT runs into some kind of a novel situation, it can turn around and ask the humans for guidance when they run into these things that they're no longer confident that they know how to deal with.
Here we go again, Dr. Scott. The humans. Ay, ay, ay. But before we wrap up, I want to ask about performance and resources. IoT devices often have limited computing power. Does combining methods make systems heavier? And how do you balance computational efficiency with intelligence?
Well, it's a great question. Hybrid systems can indeed be heavier because there are multiple components involved, but that's not always the case. Reasoning engines can be lightweight if the rule systems are small. Learning components, particularly neural networks, can be pruned or quantized to use fewer resources. So, people are running a lot of LLMs on even Raspberry Pis these days. And the other side is the componentry, the hardware is also getting more capable. There's a lot of edge AI devices that are getting a lot beefier and able to handle more computational processing. And of course, you can always offload some of the processing to the cloud if you have a lot of processing and latency isn't a really big problem. The key is just to match the algorithmic complexity of what you're trying to do with the hardware capabilities. So you're going to have to kind of go back and forth a little bit at times, but I think you could certainly implement many of these ideas today.
Thanks, Dr. Scott. And we've covered a lot of ground from reasoning versus learning, big data versus rules, neurosymbolic computing, pins, vibe coding, and reinforcement learning. I feel like my head's going to spin. Well, what is your takeaway for our viewers?
We have covered a lot of ground, and I hope I haven't blown people away. But my key message is this: don't just limit yourself to purely learning approaches or just purely reasoning approaches. You need to combine these approaches to solve the many different facets of your problem. Use reasoning to encode what you know, and use learning to uncover what you don't know. And then experiment, try different things. AIoT is a rapidly evolving thing. And my last key message is think Neuro-Resonic AI.
All right. Thank you so much, Dr. Scott. I think that's a great note to end on. And thank you so much for sharing your insights and experience with us.
Thanks, Tiffany. It's always a pleasure.
And to our audience, if you'd like to learn how to integrate these AI techniques into your IoT projects, or if you're struggling with a specific IoT challenge, don't hesitate to reach out to Dr. Scott either on the platform or on LinkedIn. And you can also visit the Knowledge Reactor booth in our virtual expo hall for more information and a free download with more information on AIoT. Thanks for tuning in and stay curious. Thanks, Dr. Scott.
Thanks, Tiffany.
And now for Q&A.